Welcome to Signal Science System subject classes. Now we're in the seventh chapter, that is Laplace transform. So in previous class we have done problems on the Laplace transform and inverse Laplace transform. So in this class, so this is the fifth video, part 5. So in this class we are going to discuss properties of the Laplace transform. We know that properties already we have discussed in the continuous time Fourier transform and discrete time Fourier transform and continuous time Fourier series, and also in discrete time Fourier series. Before writing properties, here I would like to write one time these formulas for the Laplace and inverse Laplace transform formulas. So we know that the Laplace transform, it is related to the continuous time signal. So this x of t is a continuous. So continuous time signal. So the x of s, here I am writing its Laplace transform pairs. So x of t, so this is Laplace transform. There is x of s. So the formula for Laplace transform, so this is very important. X of s equal to integral of minus infinite to the plus infinite x of t into e power minus st into dt. So this is the formula for Laplace transform. Similarly, inverse Laplace transform, that is x of t, that equal to 1 by 2 pi j, the integration, the limits are sigma minus j into infinite, sigma plus j into infinite. So it is a function of x of s. We should do the integration for the x of s into e power st into ds. So these are the formula for Laplace transform and inverse Laplace transform. Now we are going to learn the properties. So properties, in the first property, before going to the properties, here I am taking two signals, one x of t. So it's x of t Laplace transform, that is x of s. And the second, another one, continuous time signal, this y of t, I'm assuming it's Laplace transform. So that equal to, that is y of s. Now the first one, is linearity property. We know that when we are using this linearity for the addition of the two, so this linearity is nothing but scaling. We know that this is scaling and addition, additivity. These two are also known as superposition theorem. So in superposition theorem, So superposition or linearity both are same. So here a into x of t. So x of t is multiplied by a, and it is added by the another y of t. This y of t multiplied by the one constant. Then its Laplace transform also same. Same we will get same a coefficient a and x of t Laplace transform x of s plus b into y of s. So this is Laplace transform linearity. The second one, there is time shifting property. So it is very important in all techniques, all transforms. So time shifting. So in this class, while discussing properties for the Laplace transform, we can convert these properties to the continuous time Fourier transform also. I'll show you. So this time shifting, so very important. Mm. So this is very important. So x of t, its Laplace transform, that is x of s. Then time shifting. So this is t x of t minus t naught. It is a delayed signal of x of t by t naught units. Then what is the Laplace transform? This is the question. So this is the question. So what is the Laplace transform? So to proving, so we can use this formula or this for anyone. So for this case, I'm taking the first one, Laplace transform. So in Laplace transform, this is a x of s. So x of s, this is integral of, so minus infinite to the plus infinite. So x of t into e power minus st into dt. So this is formula. So formula. So based on this formula, now I'm going to find the Laplace transform for the given time shifted delayed signal. So that equal to, so integral minus infinite to the plus infinite. So x of t minus t naught into e power minus s into t dt. So we have to change this function to the our known formula. So I want to change the variable. So this is a function of the t, is it? So I want to change. So t minus t naught. I'm assuming that is tau. Tau. So dt equal to d tau. So no. So for that limits also, these are the limits for the tau, same. For the t limits, then substitute, then here also we'll get same limits. X of tau into e power minus s. So t equal to tau plus t naught into d tau. So integral minus infinite to the plus infinite x of tau, that equal to expand e power minus s into tau e power minus s into t naught. So here we're doing the integration with respect to tau. So this is a constant. So here I'm writing e power minus s into t naught integral of, so minus infinite to plus infinite. So x of tau into e power minus s into tau d tau. So this is similar to this formula, but variable here this variable is t, but here this variable is tau. It doesn't matter. So we can write this is so e power minus s into t naught into x of s. So this is the time shifting property. So x of s into the x of s must be multiplied by the e power exponential function e power minus s into t naught. So this t naught, this is delayed. This is x delayed of the x of t by the t naught units. So this is about time shifting property. So we will do the one problem based on time shifting. So x of t, so one x of t is given that equal to e power minus 2 into t minus 3 into u of t minus 3. Then find x of s. We know that the general formula e power minus at into u of t. So this is so it is one general formula that equal 1 by s plus a. So here e power minus 2, this is shifted signal. So this is shifted. So what shifted? So this is shifted to the e power minus 2t into e of t. So this is shifted. So this is shifted up this signal by the 3 units. So for this, so this is x of t. So this is x of t. So we don't take, already we have taken x of t. So this is general formula. The general formula. So for here, so in time shifting property for delayed, first e power minus 2t u of t, its Laplace transform 1 by s plus 2. And now this time shifted, so e power minus 2 t minus 3 into u of t minus 3. So that is so 1 by, so this is x of s. So s plus 1 by s, 1 by s plus 2 it is must be multiplied by the exponential, that exponential equal to e power minus, why, because it's a delayed signal, so minus how many units it is delayed, 3 units, so 3 into s, this is sc into delayed units, the delayed equal to 3. So you can write 1 by s plus 2 into e power minus 3 into s. This is the case. Now, I want to explain the property in the continuous time. So this is time shifting property. So in case of the continuous time, so that is x of t signal in the time domain, that is so time shifting property in the continuous time property, continuous time Fourier transform. So continuous time Fourier transform. So that is x of j omega. So time shifted, so x of t minus t naught, so that equal to x of j omega e power minus, so x of t minus t naught x of j omega multiplied by the exponential that equal e power minus j omega into t naught. So both are same. See, once you substitute s equals, so what is the difference between this continuous time and Laplace symbol in the continuous time? Sorry, in Laplace transform. Once you take the s equal to j omega, it becomes a continuous time for a transform. See, see here this x of now I'm going to substitute s equal to j omega. So x of, see here x of j omega into e power minus s equal to j omega into t naught. See, so same we will get both are same. So what is the difference? Difference between the Laplace and the continuous time. So in the continuous, once in Laplace transform, if you consider s equal j omega, that is nothing but the continuous time Fourier transform. So in the Laplace, we are considering real part sigma plus j omega. In the continuous time, we are not considering, so sigma equal to 0. So that equal to, so s equal to j omega. So this is related to the continuous time Fourier transform. So it is, so this is the case. Next property, frequency shifting. So are shifting in the S domain. Shifting in S domain. We will see. So this is the third property. X of t. So x of t, it's a Laplace transform that equal to x of s. Now this Laplace transform S domain signal is going to shift by s naught unit. That is x of s minus s naught. So this is the constant. So what will happen in the time domain? So what will happen in time domain? For that, I'm taking the Laplace transform formula. So x of s equal to minus infinite to the plus infinite. So x of t into e power minus s into t dt. So this is so for this now we are going to find this x of s minus s naught. Just replace the s by the s minus s naught. So x of s minus s naught. Then see integral minus infinite to the plus infinite. So x of t into e power s minus s naught into t into dt. Now expand. So integral minus infinite to the plus infinite. So x of t into e power minus st into e power. So minus into minus plus s naught into t dt. So this is the function of s and t. This is the only function of t. This is the function of t. Then we can write so minus infinite to the plus infinite. So x of t into e power s naught into t into e power minus s into t to dt. So this is equal to the x of s minus s naught. So this is the shifting in the s domain. So this is the signal in time domain. This is the signal in the frequency domain. So this is equivalent in time domain, that is equal to x of t e power s naught into t. In the continuous time Fourier transform, also same. This see x of t, it's continuous time Fourier transform, that is equal to x of j omega. So frequency shifting x of j minus omega naught. So this x of t into e power j into omega naught into t. So, so here just substitute, so x of s equal to j omega. So this is the constant in the s domain. So so that's constant. I'm writing like yes j into omega naught. This is a case of the Laplace. In the Laplace, we are considering s equal to j omega. Then so x of t into e power for s naught equal to what? J into omega naught into t. So this is, so we have taken the x equal to j omega. Once you consider s equal to j omega, so that equal to x of t into e power j into omega naught t into Laplace of x of j omega minus j omega naught. So this is the case for the s equal to j omega. So this is the case. So there is no difference. It is a very small difference, that is only s equal to j omega. Considered in the Laplace, it becomes continuous time Fourier transform. That is a case. Next property, time scaling. So it is also very, very important. So x of t, so Laplace transform x of s. So x of at. So what is the Laplace transform? See, for this derivation, so I'm taking x of t. So inverse Laplace transform, that equal to 1 by 2 pi j, 1 by 2 pi j, sigma minus j into infinite, sigma plus j into infinite. X of s equal x of s into e power s into t into dt. So ds. So just replace the t by the at, then x of at, so 1 by 2 pi j, so integral sigma minus j into infinite, sigma plus j into infinite, x of s, so s into, so a into t ds. Now I'm assuming this s into a equal to another variable that is s domain. We can take s naught. This is a variable. So ds equal to, so ds naught by a. It is better to take, already we have taken s naught is a constant. Take the s dash. Yes. Now, so 1 by 2 pi j, so integral sigma minus j infinite, so sigma plus j infinite. So x of s, so x of s equal to s dash by a and e power s equal to s dash t ds equal to ds dash by a. So for that we are getting x of at that equal to 1 by 2 pi j, 2 pi j integral sigma minus j infinite, sigma plus j infinite. So 1 by a, so we can take mod e, mod e. So x of, so s dash by a, so e power s dash t and ds dash. So this is the, so we can write, so this is a signal in time domain. This is a signal in s domain. But it just does, it doesn't matter. We can, this is another variable. So like, so yes, yes, yes. So we can take in any variable in place of the s. It doesn't change the mathematical concept. So x of t, so that, so we can write here this 1 by mod a x of s by a. So it's a very, 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 very important this property. Very, very important. Okay. Next one, convolution. So this is very, very, it is also very, very important. Convolution property. Convolution property. So time convolution in time domain is equal to the multiplication in the s domain. So x of s into y of s. So for example, the problem, one LTI system is given. So LTI system is given. So it's transfer function h of s, sorry, uh, in time domain. So h impulse response h of t that equal to e power minus 3t into u of t. And this input is given the x of t equal to e power minus 2t into u of t. Then what is the response? What is the output? unit step impulse response. Sorry, response of the LTI system. This is LTI system. So what is the output? So in previously in the second chapter, we done the convolution method that in the we solve the convolution through the graphical method. So y of t, we know that y of t equal to x of t convolution into h of t. So from the convolution in Laplace, we know that the convolution in the time domain that is equal to, so y of s in s domain that equal to x of s into y of s. So here this e power minus 2t into e of t is equivalent in s domain that equal to 1 by s plus 2 in Laplace. So similarly, e power minus 3t into e of t that equal to 1 by s plus 3. So here this y of s equal to 1 by s plus 2 into 1 by s plus 3. So to find the y of t, we need to do the partial fraction. So in that, I'm writing like this. So 1 by s plus 2 minus 1 by s plus 3. Or we can do the formula already I told you, PQ, sorry, um, Px plus Q by s plus A into s plus B, or sorry, this is x plus, so x plus A, so x plus B, it is calculated by x plus A plus B by x plus B, is it? So in that method, or substitute x equal to minus A in this numerator and denominator, that is equal to A. Substitute x equal to minus B in this numerator and denominator, you will get the B. So in that way. So now apply inverse Laplace transform. Inverse Laplace transform. Already we got the region of convergence for the sigma greater than minus 2, in this case sigma greater than minus 3. Here also same, these are the sigma greater than minus 2, sigma greater than minus 3. Then the y of t equal to 1 by s plus 2, 1 by s plus 2, that equal to e power minus 2t into e of t, and this is minus, and 1 by s plus 3 inverse Laplace transform equal to e power minus 3t into e of t. So this is the, but in graphical method, it's very difficult. It takes time. But the with the help of the convolution, the Laplace transform, first apply the Laplace, then divide the as a two functions, then apply the inverse Laplace transform, then you will get the output. So this is the importance of the convolution in the Laplace transform. Then we go for next property in previously, that is the fourth one. Now this is fifth. So this is, sorry, this is fifth one. Fifth one, now sixth. So sixth property, differentiation. So differentiation in time domain. That is, so x of t, so x of t Laplace transform, that is x of s. Now d by dt of x of t equal to what? So that equal to s into x of s. See, in simple, From this derivation, x of t equal to 1 by 2 pi j integration. I'm not writing limits. X of s e power st into ds. So do the differentiation with respect to t. So x of t. So in right side, already here we have the integration. In the internal of the integration, the differentiation, it becomes partial differentiation. So in partial differentiation, t with respect to t, this s is the constant. So in partial differentiation, do the partial differentiation with the t, uh, dou by dou t, dou by dou t e power st into ds. So that equal to 1 by 2 pi j integral x of s into differentiation with respect to t. So s into e power s into t ds. So this is already here we have written. So this is the case. So next property, so that is seventh one. So it is also similar to the continuous time. So this is in continuous time d by dt of x of t. So that equal to j omega into x of j omega. Just take the s equal to j omega, it becomes the continuous time for a transform. Already I told you. Now integration. So x of t, so x of t, it's a Laplace transform that equal to x of s. So integral of minus infinite to t x of tau d tau. So that equal to, so x of s by s. In the Fourier transform, that is x of j omega by j omega. So these are the very important. These properties also very be careful. The next property, differentiation. Differentiation in the S domain. So see x of t, that is x of s. So d by ds of x of s is what? See, so x of s that equal to integral of, so minus infinite to plus infinite. So x of t into e power minus st into dt. So we are doing differentiation with respect to s. So d x of s by ds. So in the integration, in the inner part of the integration, it becomes the partial differentiation dou by dou s into e power minus s into t dt. So integral of minus infinite to the plus infinite x of t. So with respect to s, minus t is a constant. So minus t into e power minus st into dt. So this is the d by ds of x of s. This is the case. In the previous case, in the continuous, here we got minus jt. Then the minus jt we sent to the left side. That 1 by minus j, it becomes j. So j into d by d omega x of j omega, that is equal to t into x of t. So but here there is no j. So we are taking the minus to the time domain, that equal to minus. So minus t into x of t. or we can take, we can also write t into x of t. So it's a Laplace transform minus into d by ds. So both are same. It doesn't matter. We can take minus in left side or right side. So last two theorems. It's a very important. These initial value theorem and final value theorem. Initial value theorem. First one is initial value theorem. Initial value theorem. So what is the initial value theorem? For example, say one signal x of t is a signal. Is it? So x of 0, it is called initial value. So this is continuous time signal. So x of 0 place, it is called initial value. Initial value of x of t. And its Laplace transform, we are assuming that is x of s. But this initial value theorem, it tells the relation between the initial value and s domain. So in this initial value, 0 plus or limit t tends to 0, x of t, 0 plus or 0, you can write. So that equal to, that is the relation between the time domain and the previous domain. So that equal to limit s tends to infinite s into x of s. So this is the case. So this is the limit limit. So this is theorem. Next, last final value theorem. Final value theorem. So here also x of t is a continuous time signal. This x of this is called steady state value. Steady state value or final value. Final value of x of t. Then the final value x of steady state value, that will limit t tends to infinite to the x of t. So this is equal to the limit s tends to 0 s into x of s. So for the initial, here in limit, you should take the s tends to infinite and x of s must be multiplied by s. For the steady state, here we have taken the s tends to 0. So that is the difference. So these are very, very important theorems. So it is about properties of the Laplace transform. In next class, we are going to discuss the problems based on these properties. Thank you.